Good afternoon, delegates and invitees. So now for this session, we have Professor Mahendra Singh, Professor of Civil Engineering at IIT Roorkee as a chair. He is working in the areas of landside analysis and mitigation, stability of soil and rock slopes, rock mechanics, strength and deformation behavior of jointed rocks and rock masses, tunnels and underground excavation. He has supervised 11 PhDs and 9 are working now. He has published more than 50 journal papers and investigator for several NDMA projects. And we welcome Professor Mahendra Singh. And next we have co-chair, Dr. Kaustu Chatterjee is assistant professor in the Department of Civil Engineering at IIT Roorkee since June 2016. He has done his MTech and PhD from IIT Bombay. He was a postdoctoral research scholar in Kyoto University, Japan. His research interests includes geotechnical earthquake engineering, soil dynamics, and liquefaction. He has authored more than 25 research papers in journals, and he has supervised 7 MTech students and currently supervising 5 research scholars for PhD. He is recipient of G.A. Leonard's Best PhD Thesis Award from IGS, John Carter Award from I.I.Sc MAG, Best PhD Thesis Award from IIT Bombay, and ISSMGE Foundation Grant UK. We welcome Dr. Kaustu Chatterjee. So now I request chair and co-chair to take over and start the proceedings. Thank you.
Thank you, Professor Raghuveer, and welcome everybody, the participants and Professor Hazarika and delegates. So it's my pleasure, and we thank the organizers for giving this opportunity. So let us start the session, and as I see, there is one SOAP lecture, and there are 5 papers. So all they are presenting, all the 5 papers are. They have given their consent.
Yeah. Yes. But they are yet to join. 3 of them, 2 of them are there. Others will be joining now. I will get them.
So yeah. I hope all 5 will present.
Yes.
Okay. Then we are keeping 30 minutes for this lecture.
Yes, SOP lecture 30 minutes plus 5 minutes discussion, and all other papers 8 minutes plus 2 minutes discussion.
Okay, that's already decided. So I think we can start, and I request my co-chair to kindly introduce the speaker and then invite him for the talk.
Thank you very much, Professor Singh, the chair of the session. So it gives me immense pleasure to introduce Professor Hemant Hazarika, who will be giving the SOP lecture for this technical session. Okay. Professor Hazarika is a professor of Geo-Disaster Engineering at Kyushu University, Japan. His fields of specialization are geomechanics, earthquake disaster mitigation, and geo-environmental engineering. In recent years, he is developing technologies for climate change adaptation from the geotechnical perspectives are the urgent need of the society, and the research is focused on those. Developing research methodology which incorporates and combines these 2 important aspects that the present-day society is confronting, that is disaster mitigation and environmental protection, is one of the most important goals of his research group. His research areas include field survey and testing, model testing and the simulations, element testing of natural and recycled materials, characterization of those materials, developing disaster mitigation systems using drones, IoT, and artificial intelligence. Aim of his research is to make best prepared for the immediate and present dangers facing the global community through geo-disaster risk mitigation. So with this, I now give the stage to Professor Hazarika to start his special lecture. Thank you very much.
Okay, thank you, Dr. Chatterjee, for the nice introduction. Before I start, I'd like to thank the organizing committee of 7th International Conference on Recent Advances in Geotechnical, Earthquake Engineering, and Soil Dynamics for inviting me to deliver this lecture. This is the title is Forensic Evaluation of Long Distance Flow in Gently Sloped Ground during the 2011-18 Sulawesi earthquake in Indonesia. Before I start, I'd like to acknowledge my co-authors, Mr. Divesh is a PhD student under me right now. Dr. Kyota from University of Tokyo, Professor Okamura from Ehime University, my former PhD students, Dr. Pasha from Image Eye Consultant in Tokyo, and Dr. Nurdin from Tadulako University in Indonesia. Well, the long distance flow that I mentioned in my title is what is that long distance flow and why that happened in a very, very gentle slope, for example, of slope of gradient 1 to 3%. Okay, this is just an image of the flow slide that took place after the 2018 Sulawesi earthquake in Indonesia. I'll just play this video. You can see what is happening, what has happened after the earthquake. This whole, the ground, they flow like this. So you can see the original, the city was like that, the town, part of the city. And after the earthquake, due to some phenomena, the whole part is gone. So this is the topic of today's lecture. Okay, so before I go into the details of the investigation that we conducted in Palu, let me give you a brief introduction on the earthquake itself. Before that, I think many of you may not know what is Sulawesi. As you know, Indonesia is a country of many islands. Main islands are Sumatra, Java, Bali, and Kalimantan, and this Sulawesi in the eastern part. So this is another island, and the Palu is one of the biggest city in the island, and the earthquake epicenter was about 80 kilometers from this Palu city. And the flow slides took place in Palu city. The earthquake was of moment magnitude 7.5, and it took place in September 28 in the morning with a peak MMI intensity of about 8. And it was caused by the shallow tectonic activity of this Palu Koro fault. So it's a fault-induced earthquake. This is the north-south component of the acceleration recorded by the stations installed by JICA of Japan, and this is the east-west. As you can see, the acceleration itself, the peak ground acceleration is not that high. It's about 200 gals to 300 gal. And this right-hand side, you can see the spectral acceleration versus the period of vibration. And from here, you can see that the short period between 0.1 to 1 second components are predominant. So that means not many buildings are going to be destroyed or damaged by this kind of earthquake. And mostly it's a geotechnical damage. Let me share you a video taken by some local people there when the flow slide took place. So in fact, the person is moving in a car in the opposite direction of the flow. Okay, that you have to remember. So you can see how it is flowing. You can see the red house actually. It looks like flowing, but actually it's not. Because of the relative velocity, okay? Now you can see this electric poles here, which is moving, okay? This one. This is this actually what happened after the earthquake. This is not during the earthquake. Okay, so this kind of flow took place in 4 different areas in the Palu city. One is from top, it is Balarwa. This is the Palu Koro fault, and this is the Palu river. Actually, I'm sorry, there are some characters in Japanese. Then one is Balarwa, one is Petobo, one is Chonoge, and another one is Sibalaya. The size represents the magnitude of the flow area. So you can see that the topography of the area, this is Petobo, Chonoge, Sibalaya, and Balarwa, Palu Koro fault. There is another normal fault. This is the active fault. Okay, there's another normal fault passing through this area. This is the Palu River, and it's mostly the alluvial fan, and there are mountains on both sides, both east and west banks of the flow areas. Okay. About this, I'll come back later. So after the this flow slides, which claimed about 1,700 lives, total calamities of this earthquake, about including the tsunami, which took place along the coastal area, about 2,100. Okay, so these landslides or the flow slides itself claimed more than 1,700 lives. So after that, the JICA, Japan International Cooperation Agency, formed an advisory team with Professor Ishihara, Kokusho, Yasuda, Tohata, Okamura, Kyota, and myself. And we went to the site several times. And I'm going to talk about those investigations and results of those investigations. So from our university side, me, Dr. Manafi, and my Indonesian student, and Divesh, we joined, and from University of Tokyo, Dr. Kyota, and Professor Tohata, also from Ehime University, Professor Okamura. We conducted the survey in 3 different periods, in 2018, 2 times, and 2019 once. We wanted to go in 2020, but because of the COVID-19, we could not go. We targeted these Balarwa, Petobo, Jonog, and Sibalaya, these 4 areas. Of course, along these coastal lines, there are tsunamis, not due to the earthquake, but due to the landslides along these coastal lines, and that created tsunami. So we basically did some drones survey and performed PDCPT, portable dynamic cone penetration test, and conducted trench survey and collected some disturbed and undisturbed soil samples. The purpose is to determine what is or what are, we still don't know actually. That's why I put both is and are, the mechanism of such unprecedented long distance flow in such a gently sloped ground. Okay. Today, because of time, I'll just focus on two areas, Jonoge and Sivalayas, which Jonoge is located about 6.7 kilometer from this Palukoro fault, and Sivalaya is located about 3.6 kilometer. So let me talk about Jonoge first. This is the flow site area. This is before the flow site, before the earthquake. This is after the earthquake. Okay. This blue one, I'm sorry, still in Japanese. This is the water channel. So most of one of the peculiar characteristics of this flow site is that most of the flow site took place around that. 3 locations they have a water channels on the top of the start of the flow. So it covers in Jonoge, it's the largest one, covers about 3 kilometer length and 1 kilometer width area, and the slope is just 1%. Is the most gentle among the 4 areas, and irrigation channel here is just above the flow site, which also got damaged, and the flow site caused the overflow of the river downstream here and caused flooding in the neighboring areas. These are some of the photos. As you can see, this is the unlined irrigation channel. They were badly damaged during the earthquake, and about 3 to 4 meters of depressions, subsidence of the soils in the area due to the flow. We also observed some huge sandballs in the part which were intact, which were not damaged during the flow slides. This is about 2 to 3 meters diameter sandballs. As you can see from here, it's a very, very flat area. It's not sloped ground. On the start of this flow, near the cliff, we could see some geology of the area. Here you can see top is silty clay, then sand, some silty clay, then gravelly sand, then silty clay. If I pick it up, these 4 layers, then I can say that top part is the low permeable layer, then we have a sandy layer, then low permeable layer, and gravelly sand layer. Okay? So one of the probable mechanism of this kind of flow may be due to the formation of water film. I'll explain to what is water film later. Okay, due to this existence of this kind of low permeable layer, which acts as a kind of capped layer to prevent the liquefied soil to go up and forms the water film. But liquefaction alone cannot explain this phenomenon, because normally we have a lateral flow due to liquefaction, but it can be up to few meters, not like few hundred meters or few kilometers like here in this case. These are the situations in Jonoge, as you have seen in the videos, the red house, which looked like moving. Actually, in fact, it did not move. As you can see, this is a red house, which did not move. You can see the foundation shape. Foundation here, the exposed one, about 70 centimeter. We don't know, maybe the below you have 2 to 3 meters good solid foundation. That's why probably it could not move. The flow side, the thickness would have been less than the thickness of the foundation. So this is the flow direction, and you can see dot of deposition around this area. We conducted some penetration test close to that. So the surrounding houses were swept by more than 300 meters. You can see this is the 400 meters. So most of the houses, they were moved during the flow sites. So we decided to conduct several dynamic cone penetration tests in both in the failed area as well as outside the flow area. So these four are inside the flow area. This one is outside the flow area. First, about the PDCPT1 is the outside one, then 2, 3, 4, 5. Okay, 4 is near that red house. So this is the result from the location PDCPT1, which is outside the flow area here near the cliff, and these are the elevation of the area. And you can see here that groundwater level was about 2.3 meter when you conducted the test. And you can see that below this, up to about 2 meter, this is the converted N values, this is the penetration depth. The N value is relatively high, but below that you can see a very weak layer. Okay, and top of that there is a strong layer which acts as a cap layer. So there is a strong possibility of sliding on the top of this weak layer, which is below 2 meter. And let us compare the results at the outside the flow area and inside the flow area, which is about 494 meter apart, and with a average gradient of about 1.9% here. So one is outside, one is inside. So if you compare that, then this is outside one, which I already described. This is the inside one. That means this part is already gone, right? This part is flowed. So that means practically we are conducting the PDCPT from this ground surface. So if you compare this and this, they're almost exactly same. So that means, and below that, there's relatively steep ground. That means there is the continuity between the results of PDCPT at location 1 and location 2. So let me now move on to the another PDCPT location, which is close to a bridge, which is actually there's a river. It's almost dry that time. There's a dry season in Indonesia. This bridge is completely collapsed. There's a road going there. Actually, whole road is gone. So we conducted some PDCPT tests there. This is the elevation, and also we conducted a PDCPT one near the red house, which was not moved, and one near this blue house, which was moved by about 300 meters. So near the red house and near the bridge, near the red house and away from the red house. Okay, so all this PDCPT conducted in those locations, they show that, except here, this is near the river, so of course the N value is very less, but other than that, below about 4.5 to 5 meters, the N value is quite high. So again, we could confirm the existence of weak layers in all the 3 locations. And the soils were mostly silty sand. And after that, this is our second investigation. And on our third investigation, we also conducted further PDCPT in some other location. Our previous one is 1, 2, sorry, 3, 4, and 5. Okay, and we decided that we should also conduct some PDCPT along this line and some PDCPT along this line because there are a lot of deposition in this area. So yellow pins are the new PDCPT and the green ones are the old, which I already described. So here, if you compare the new one with the old ones, okay, like we named J07, J08, J0 means Jonobe, then we can see that along the orange line here, okay, the thickness of the weak layer varies between 2.5 meter to 3 meters below the ground surface, existing ground surface. Okay, and this might be due to presence of the residual soil because it was this whole area flowed, so there are some residual soil deposits, and we started from the existing ground surface. So initially, of course, this weak layer should always be there. So this is all mud flow deposit due to flow failures. Also, in another location along the green line, the thickness of this weak layer is increased by about 4 meters, whereas our previous survey showed that it is between about 2.5. So it's between 2.5 and 4 meters the weak layers exist where displacement because of the residual soil deposit. Okay, so displacements were limited in the upstream of the flow side. Okay. And we also got some data conducted by Indonesian researchers on resistivity of the resistivity-based analysis of in a particular location, which is about 1.3 kilometers from the water channel that I described before. This is the water channels. So they couldn't do any resistivity analysis here because of the construction activities. So, and we also conducted some PDCPT survey there, and we found that these are the results, and you can see that this red line, red areas, these are the resistivity in ohm. So this rock and weathered rock, the blue one, we could see the existence of artesian aquifer, and some light blue, which represents the loose sandy sand and sandy granite. And our PDCPT results also confirm the existence of the loose soil layer at the top, and also somewhere around 2 to 2.5 meter location. Okay. So these are some confirmation of the resistivity analysis and PDCPT results, which are showing similar trend. Okay. Also, we collected some samples from different layers, J1, J2, J3, and based on the grain size distribution curve, we can say that most of the salts they were collected are liquefiable, because these are the standards given by Port and Harbor Research Institute of Japan, and potentially liquefiable and most liquefiable. You can see that all the soil samples fall within these curves, and also they have very high fines content. So that means these higher fine contents make the soil very contractive and flowable on the contractive side of the steady state line. And that was the research conducted by Professor Kokusho in 2019. This I'll skip because of the time. Then coming to Sibalaya, another location. This is the Sibalaya before, and this is the after. You can see that this road is completely broken, not really broken, it's damaged and moved by about 300 meters. There's displacement of the road. more than 350 meters, in fact. And we conducted some trench survey. We dug about 1, 2, 3, 4, 5 trenches on both sides of the floor area, and also some PDCPT testing we conducted. This is the trench actually near the cliff. You can see here, if I focus on this area, the upper part is sandy gravel, then low permeable layer, then sandy gravel, then sandy layers within the about 5 meters from the top. So we could confirm the existence of a low permeable layer, which is sandwiched between the sandy layers. This is very common characteristics of most of the trenches. We also conducted the PDCPT test, and the PDCPT test was conducted actually right here. So this is the cliff. So practically these are deposited salt. So of course we could see very low converted N values. Then after that, below 1 meter, we could see probably we had caught some gravel. But our Ehime University group, they conducted similar PDCPT in somewhere near that, but somehow they could get different results. But ours, we could not proceed further because of the and because we encountered some gravel soil. And next, PDCPT, another one next to Trans 4. Our results and their results are almost similar. You can see last year between up to 2 meters, then it is some gravelly layers, then again some sandy layers and things like that. So this is again sandy layers, low permeable layers, sandy gravel, and sandy layers. And outside the floor area, we conducted another PDCPT test here, and there again we saw that the N value is very high on the top. That's why it didn't fail. And below that, we found a very weak layer. And again, on Jonoge, we collected many samples, S1 to S5, and these are the ranges of the potentially liquefiable and most liquefiable salts. And you could see that some of them fall within these ranges, and the fine contents are very, very high, which means they're likely to liquefy and cause the flow. And from the trench, again, trench 3, we could see similar trend, gravelly sand, low permeable layer, gravelly sand, and sand. So always a low permeable layer sandwiched between the sandy layers. Similarly, in another trench, trench 4, we could see similar trend. Okay? Always a low permeable clay silt or some kind of low permeable layer exists. So what is or what are the mechanisms? Okay. First, you have to look at this geology of Sulawesi. Is in the central Sulawesi, where Petobo, Jonoge, Balaro, and Sibala are located, consist mostly of quaternary sediments. That is another problem of that area. And also the topography. I'm sorry, some of them are in Japanese, but I'll explain to you. Here, you can see that this is Petobo, this is Jonoge, and Sibala. This is the Palu River, and this is the fault, approximate location of the fault. You can see there's some old alluvial fans there, and some new alluvial fans were formed with times. And most of those flow took place near the new alluvial fans. You can see it's Petobo here, Jonoge here. Okay. So this is one of the reasons probably why this area failed. Okay. And we also confirmed the presence of artesian aquifer and also low permeable cap layer, and liquefaction of the sand layer below those cap layers can be thought to have produced the fluidized flow. However, it is very difficult to explain such long distance flow from the viewpoint of liquefaction alone. So what we could confirm through this forensic investigation is that the flow occurred in a confined aquifer, and there are some traces of liquefaction outside the flow zones, and the gradients are very, very small, 1 to 4%, and the flow distance were few hundreds of meters to kilometers. And these are not possible to explain using lateral flow due to liquefaction. So what we can think of is that they're very special soil, some kind of phenomenon like quick clay might have taken place, and there are inclined layers within the geology and formation of water flames and existence of artesian wells. These are some of the hypotheses of long distance flow. We in the JICA technical committee came up immediately after these disasters. We have this liquefaction here, then flow started to taking place, then also the artesian groundwater came up, destroyed the cap layer, and led to the flow of the large distance fluidized flow of these areas. There are many hypotheses, but I'm not going to deal with all the hypotheses, but definitely we found that the impermeable layer, existence of impermeable layer, and probable water film generation in the below these layers. This is one of the hypotheses brought by Professor Tohata. As I mentioned, there are a lot of alluvial fan deposits there. Groundwater were plenty there, and there is a clay cover here, and there are many water springs even before the earthquake in that area, and water pressure under cover were more than the hydrostatic water pressure, and during the earthquake, this clay layers were destroyed and led to this kind of fluidized flow. This is Professor Tohata's hypothesis, but we cannot still confirm. So also from water film point of view, we have many silty layers here. So we have sandy layers. So there is aquifer here before the earthquake, and during the earthquake, the liquefied layer could not break this cap layer, and they formed a water film. And in addition to that, the aquifer water came up and led to this kind of large distance flow. This is another hypothesis. So maybe there are multiple water flames which were formed below the clay layer due to liquefaction and leading to the loss of shear strength. So what is water flame is that we just did some one-dimensional column test. There's a clay layer here, sandy layer here, sandy layer here. We just gave an impact using this hammer, and you can see that there is clearly the water layer forms below this clay layer. You have to observe very carefully. Okay, I'll put this video. You can see there's a water film here. There's a clear formation of film of water here. Okay, so this is probably what happened in some areas of Nepal. Okay, actually, Professor Koksho did a lot of studies before that. He conducted some model tests on water film. You can see this clay layer, two double clay layers, the embankment here, one single clay layer, sloped ground. You can see here, you can see how the flow is taking place. Without this ground movement, this ground only move. Similarly here, can see only above this cap layer, the movement is taking place. So this is what is water film. So my final conclusion is that we still could not arrive at any definite conclusions because this is very complicated phenomenon. So we have to look at the structure of the soil, effect of the non-plastic fines in the sandy, liquefiable sandy layers, and effect of the large strain because this after the flow, they're moving at a very faster velocity. So that is a large strain phenomenon. So we have to decouple it from the pure dynamic phenomena before during the earthquake. Then structure of the decay layer, whether they're continuous or discontinuous, and the thickness of the cap layer, how thick they are, and effect of the potential head on the long distance flow, because that head is going to affect the long distance flow of the area, and we have to quantitatively evaluate such a long distance flow either through numerical simulation or through the model shaking table test. We conducted many shaking table tests. So far we haven't succeeded actually to simulate the condition, and of course we have to produce some hazard maps for such disaster in the future in those areas which are prone to earthquake. These are some of the publications me and my PhD students, Rohit, has published, and you can go through it. And I like to acknowledge different people from JICA and Indonesian Geotechnical Society, different universities within the Sulawesi Island, and some consulting people from Japan and also students of different universities in Indonesia, along with Professor Shihara Kokusho, Professor Yasuda, and Professor Tohata and Dr. Takaya from JICA for their support towards this research. Okay, these are our teams during the survey taken by drone, and thank you very much.
Thank you, Professor Hazarika. It was very interesting talk, interesting presentation, and there are so many aspects. The phenomena is very, very complicated, and the initial part, right from initial part where you discussed a lot of things about the penetration test, and then you showed those experiments, it gives a very good idea. So before I open the floor for questions, so just one thing, one question, or if this kind of the thing is there, means what are the mitigation measures? Is there any way means these kinds of the problems could be solved?
Yeah, good question. Actually, that was the problem with JICA. That was the main purpose of JICA. What is the mitigation measures to be adopted? But we still don't know the mechanism. So unless we don't know the reason, we cannot give any medicine, right? Just like a medical doctor. So that was still the problem actually. But one thing we can do is to that area is where the groundwater level was very high. Okay, the existence of aquifer. Okay, there are a lot of aquifers and easily you can pump water actually. So one of the mitigation measure that time we thought of is the pumping out the groundwater. Okay, to prevent further
Relieve the pressure.
disaster in the future earthquake. Okay, that is one thing. Or put some drainage pipes to drain out the water during the earthquake. Okay, to dissipate the pore water pressure and prevent liquefaction. Yes. Yeah. As of now, we can think of only those. Yeah.
Okay, thank you. Professor Raghuveer, I don't have access to the question answer, but if there is any question answer, Costa, can you read few questions?
Yeah,
So
yeah.
there are no question answer or anything in the chat also.
Okay. Can I have one question, please?
Yes, yes, sure.
Professor Hazarika, very interesting presentation and very interesting study. So is there any history of earthquakes earlier, and which season this took place? Any idea?
In that I mean that area or somewhere outside outside Indonesia or somewhere in the world. I mean,
Okay.
in the Niigata earthquake also, where the phenomenon of liquefaction was first, I could say, invented. Okay,
Mm.
we could say invent or discover. I don't know. Liquefaction was there, of course, from uh, any earthquake liquefaction takes place, but the research community started looking at the aspects of liquefaction only after Niigata earthquake. Okay, there
Oh.
are a lot of building damage. Even in Niigata earthquake, there were some long distance flow, but not like this.
Mm.
Okay? Not like of a few
Yeah, this
hundred
is quite
kilometers.
far.
This is 500 meters, 1
Yes.
kilometer, 1.5 kilometers,
Yes.
quite far actually.
Mm.
In Niigata earthquake, about 100 to 200 meters, there are some flow. Okay,
Mm.
that was there. But so far, nowhere in the world we have seen such long distance fluidized flow. That too in a very, very gentle slope, is very 1 to 2%, maximum 3% of gradient. So yeah, we have no
So
idea. Yeah.
before actually finding out the mechanism behind this, I think it is urgent to find out any such localities are there in the similar place.
Yes,
So that is more
exactly.
important to find out and move the people from
Yeah,
there. Yeah.
exactly. That's why I put in my last conclusions is hazard maps. Okay, so you have to find those potential area and create hazard maps for those areas. That's important. Yeah, you are right.
Thank you.
Thank you.
Thank you, Professor Hazarika.
Thank you,
So
Professor Singh. Yeah.
thank you very much. Very interesting. So can we have one or two questions from the what is the mechanism? They have to put it in chat box.
Yeah, they will put it in Q&A chat box. Only
So
then
there is
you
no
had to
question
read
there.
out. Yeah.
There is no question there.
There were no questions in the chat box though.
Okay. Anybody in the panelists, if they want, they can ask among the present.
Okay, if there is no question, thank you, Professor Hazarika.
Thank you
Thank
very
you very
much.
much.
Thank you very much.
And thank you very much, and we
Thank you.
appreciate.
It was.
So let's go to the next
Thank you.
paper. It is studies on geosynthetic reinforced retaining wall under seismic loading, and it is being presented by Ananya Srivastav from Madan Mohan Malviya University of Technology, India. So I request the presenter to go ahead.
So, a very good afternoon, everyone. I'm Ananya Srivastav, presenting my paper, which is study of geosynthetic reinforced retaining walls under various loading. I am from Madan Mohan Malviya University of Technology, Gorakhpur. I'm an MTech student with a specialization in seismic design and earthquake engineering. So, first of all, I would like to give you all an introduction, basic introduction, that for increasing the shear strength of our soil, we need to provide some kind of soil reinforcement in it. And in the form of soil reinforcement, we can add geosynthetic layers, we can add soil nailing, or we can add geofoam, geopipes, etc. So MSC wall is basically mechanically stabilized earth wall, which is a combination of compacted soil and reinforced materials. MSC wall is a basic earth retaining wall which can be built in a tiered retaining wall system. Tiered means a whole wall, supposedly which is of 12 meter in height, can be divided into 6 meter each, with providing an offset distance of a desired value. So when we provide or when we make a tiered wall system, there are certain benefits which we would be discussing in the upcoming slides. So historical overview, I'd just like to give you a basic historical overview, which means that in 1971, Henry Vidal, which is also the father of geotechnical engineering, he gave a few FHWA guidelines, and then there were a few more researches in 1972, 1980s, and 1990s. So basically, in 1990s, we saw a dramatic increase in the use of geosynthetic reinforced walls with the introduction of segmental retaining walls. Segmental means that we'll be providing certain segments and building it in tiers rather than building a single high monolithic wall. So this is a very common design of a geosynthetic reinforced retaining wall. Then I like to give you what is the basic concept behind it. So if you can see in these figures, we have facing panels which are generally rigid in nature. We have a backfill soil and we have soil reinforcements. So facing systems can be of any kind, like segmental. They can be dry cast modular blocks. They can be welded wire meshes. They can be any kind of gabion facing, or even geosynthetic facing if it is rigid enough, and then post construction facing. So if you see in this diagram, the next diagram, we have a single tiered conventional wall. Its benefits are least space, then least adaptable, and lowest cost. Then for two tiered walls, if you can see, we have one wall, then again redivided into upper and lower sections with an offset distance in between. So what this present study does is we see the performance of a two-tier wall. Each is having a height of 6 meter, and we compare it same kind of wall with same kind of geosynthetic reinforcements with a high monolithic wall of 12-meter height. And then we are varying its reinforcement length under static and seismic loading conditions. So the guidelines that we have followed are FSW recommendations, and for the offset distance, we've taken the case where D is equal to HM. HM means the total height of the wall. 1090 minus phi r. Phi r is the backfill friction angle. In this case, the offset distance is large enough so that the walls do not have any kind of interaction over each other, and they can behave independently. Then my geosynthetic material is taken as an elastic material which can bear tensile load. My backfill model is Moore Coulomb model, and the interface values that we have taken is zero point 0.8 for soil and for soil and geosynthetic interface, and it is 0.65. So this was my design for the monolithic wall. Here we have facing panels, we have geosynthetic reinforcements, we have a leveling pad. Okay, then we have geogrid. Each spacing between the geosynthetic reinforcements is 0.6 meter. Then this is the tiered wall system. I redivided the whole 12-meter wall into 6 and 6. That is, H1 is the high upper wall and H2 is the lower wall. Each having its own leveling pad, having an offset distance of 8 meter again, which is high enough, which is large enough so that no interaction of these walls takes place, and each wall behaves independently. So results I come to. So when we talk about the two-tiered wall system, you can see the failure of the wall begins at the leveling pad, which creates a single type of wedge, which is slightly interrupted in the uppermost wall system also. So first figure is when KH, that is the horizontal seismic acceleration factor, or the coefficient of horizontal seismic acceleration is taken as 0. How I provided the seismic intensity or seismic variations is just by changing this factor. So first diagram represents when KH is equal to 0. Second diagram represents when KH is equal to 0.12. Then third is 0.24. Fourth is 0.36. So in this comparative figure, you can see as soon as the seismicity is increased in tiered wall, when there was no seismicity, it showed more failure. But when we came onto two-tiered wall system here in this, as soon as the seismic intensity is increased, what happens is the walls show a little bit of less failure than when compared to a similar kind of wall, which is monolithic in design, that is total 12-meter height of the wall. See here. If you compare both the figures, earlier figure of the two-tiered wall system and this wall system, what happens is the leveling pad is distorted, the whole soil sinks down, as well as two wedges are formed, and also the slidings of the wall and overturning of the wall takes place. Then if I compare the factor of safety values, which have been derived by a numerical modeling tool at KH is equal to 0 for both these kinds of walls, by varying the reinforcement length and height of the wall, that is L upon H. I would like to tell you all that according to FHWA guidelines, the generalized length of the wall under normal conditions are taken as for the geosynthetic reinforcement at 0.7 H. And then for seismic condition, it can go as high up to as 1.1 H. So I varied all these values starting from 0.5 so as to see what kind of factor of safety I am getting. So in this case, at KH is equal to 0, you see it is above 1.5, still satisfactory. If the first figure is for two-tiered wall and second figure is for monolithic wall. Then this factor of safety increases as we go further up to 1.7, and then in this case of monolithic wall, it increases from 1.5 to 2.2. Now this figure, this is the exact values that I was getting. This may seem a little bit flashy, then why not to construct my monolithic wall? The reason behind is that you need to give a very deep excavation. Now for walls which are as high as 40-meter walls, you cannot provide such backfill values and backfill soil transportation costs. Under such situations, construction of a tiered wall would still be beneficial. So what this graph is aimed to show is that the tiered wall also gives satisfactory values which are high above the benchmark as provided by FHWA. Hence, they can be built as well. So I weighed all this reinforcement length where H was 12-meter for monolithic wall and then two-tiered wall, H1 and H2 both have 6-meter. At KH barabar 0, I gave the reinforcement length as 14.4, which is 0.7. Then I gave L1 and L2 in case of reinforcement lengths for two tiered walls as 4.8 meter each. So as KH was increased, I also varied my reinforcement length for the wall system. For the monolithic wall, it was kept constant, but for the tiered walls, it was increased. So conclusions that I derived from this study are that the stability of the reinforced soil retaining wall and its mode of failures with variation of the geogrid length can be seen in two-tiered walls also and monolithic walls also. Both of these walls are giving good results. So any kind of these walls under certain topographic conditions or geographic conditions, we can build a two-tier wall system. So whenever there is a case, like in my second conclusion, whenever you construct a wall like 40-meter high, 50-meter high, there has been constructed some walls in Texas, USA, where there were these walls such high, so we can construct a two-tiered walls. And the FOS value shows a very minor distance. And again, the two-tiered walls are very easy to construct. Less backfill material would need to be transported. Less excavation area would be required. And then again, as the FOS increases with the increase in L by H ratio and decreases when KH increases. So all these observations give us a compound brief about proving the fact that two-tiered walls can be beneficial as well, and more research needs to be done in future on this. So here, these are all my references that I took.
Thank you, Ananya. You have finished exactly within the time which was given to you. So now, now the floor is open for a few questions. Professor Costa, is there any question in?
Yes, Aranya, can you go
Yes,
back
sir.
to your, yes, just one few questions. Can you go back to your slide before the conclusion? Can you please go to the slides before the conclusion where we have given that for the monolithic wall and the two-tiered wall, what is the optimum length required, right? That slide.
Are
Yes.
you talking about this slide?
Yeah. So
Okay.
in this case, the reinforcement length that is 14.4 meters. So as we see that from the static case, if we're going to the seismic conditions with KH is equal to 0.36, we have seen that for the monolithic wall, you have kept the reinforcement length as constant. What is the reason behind this? Why it's constant? Because as we are moving from the static to the seismic conditions, my seismic force is going to increase, right? So do you
Yes.
think the constant value of the reinforcement length will take care of it, or this also needs to be increased?
It is when I move to two-tiered wall system.
Yes, Ananya, can you please say? Yeah, I think you lost connection in between.
The seismic conditions, we need to provide a little bit of more reinforcement.
Yes, okay, but for your case, from 0 to 0.3 is almost how much? Quite a high amount. Your L remains constant. So, what is the basic logic behind keeping the reinforcement length as constant?
For monolithic wall, see, I am taking constant value of the reinforcement, but in two-tiered walls, I'm increasing because I need to combat with the seismicity conditions. Okay.
Okay, just think
And this is
over it.
totally upon a designer because there are no specific guidelines.
Which guidelines you have followed? Any particular codal provisions is there?
Yes, FHWA, Federal
FHW.
Highway Administration. Yes.
Yeah, that I know. But basically, okay, this is just, you can just discuss this with the supervisor. Okay, this particular aspect.
Okay,
Okay,
sure.
okay,
Is
Professor
there
Singh,
any
I am
other?
done.
Is there any other question, Professor Costa, in the chat?
No other questions from my side.
Can I have one question, please?
Yes, sir, please. Yes, Professor Rao.
Yeah. Can I have one question, please?
Sure, sir.
Yeah.
Yes.
Miss Anand, serious concern about this. See,
Okay.
basically, this MSC walls have come up, in
Yes,
urban
yes.
areas, basically to save the footprint. Now,
Yes, sir.
if you go for this two-type wall, your footprint you are going to increase. I don't know
Carbon
whether the
footprint.
savings you thought of making by making into two-tiered wall, offshoot the kind of benefit supposed to get.
So, sir, you're talking about like if I'm constructing a two-tiered wall system, my carbon footprint would be increased.
Not carbon footprint, the
Then
space footprint of
spacing,
the land required, particularly in urban
land required.
areas. Yeah.
Okay. Sir, see, whenever I'm talking about an MSC wall, again, I would say it is totally upon the discretion of the designer. Whether you construct a monolithic wall, whether you construct a two-tiered wall system. Suppose you have a hilly area with a kind of a rock bed formation, fine. In that case, would you think that excavation of a rock bed would be easy, or excavation of such deep excavation is possible whenever you're constructing a very tall wall? You would require more manpower, you would require more energy power, again increasing your footprint. Instead, if I construct a tiered wall system, whether it is two tiered, three tiered, or multi-tiered, again, then we would require a little less effort, whereas this tiered wall system is giving us the similar kind of beneficial results. Okay, only just I would like to tell you all that whenever we decide the offset distance, that is the distance between each tier, it is basically dependent on three factors. Here, for my numerical modeling purposes, I have chosen as 8 meter, which is very high. But again, it is again upon my discretion that I can reduce. So all these three walls will face the consequences. All these three walls will start to interact with each other. Yet their performance wouldn't be hindered. Still, they would be giving same kind of FOS values, would be performing better, same kind of serviceability criteria, safety criteria. So why not to construct it in a tiered fashion?
Okay, thank you.
Okay, is there any other question, or we can go ahead, Professor Costa?
There are no other questions. I think we can go ahead for the
Okay.
next presentation.
So let us go for the next presentation. Now the next presentation is again from Madan Mohan Malviya University of Technology. It is by Mr. Sagar Jaiswal, and the topic is numerical studies on the behavior of slope reinforced with soil nails. So may I request Mr. Jaiswal to go ahead with.
Good afternoon to all the panelists present over here. The topic of the presentation is numerical studies on the behavior of soil slope reinforced with soil nails. This paper has been authored by my colleague, Mr. Akhil Pandey, myself, and my guide, Dr. Veena Bhushan Chauhan. I would like to start with the introduction. That what is soil healing actually? Soil healing is a technique in which we provide in situ hollow steel tubes or high strength HISD bars to provide improved factor of safety of the soil slope. It is a in situ ground improvement technique. This is basically a kind of reinforcement, soil healing reinforcement. It can be performed in like two ways: horizontally or slightly inclined pellet reduction of tensile strain that is produced in the soil slope during the failure. This is a kind of passive structural inclusion to stabilize the stable slope. There are basically two regions are generated. One of them is active region, and the second one is the passive region. In active region, the moment of the soil failure, soil mass takes place, and the passive region is the region in which the wetted portion of the soil nails present, and there is no movement at all. The tensile forces in the soil nails is passive inclusion, which raises the deformation of movement of the soil in active zone. uh, the tension in the soil nails actually helps in the reducing the slip circle and driving shear force that causes the failure. Here's a brief lecture review. Uh, Soil nailing can be used for slope stabilization or expansion of rail or road embankment. This may be this may be also utilized to temporary or permanent excavation in problematic regions. Here, few benefits which I would like to uh, throw some light on. These are relatively quick to perform, inexpensive, and sustainable compared to other practices to stabilize the slope because it is less disruptive to the traffic. Soil laying basically reduces the displacement of the soil layers and increases the factor of safety of the overall system. Here, a few research gaps that I would like to discuss. Only a few studies have considered the seismic forces, that is the we can see the horizontal ground acceleration and vertical ground acceleration, but basically in this study we have used only the horizontal acceleration values to simulate the earthquake forces. The shear forces in the bending moment in soil nails are conventionally unnoticed in the design procedure, and we have also studied this thing in this paper. Moving to the numerical modeling, I would like to show this is the soil nailing length, and this is the slip circle that formed during the failure. This is the spacing between the soil nails. Here is the beta value. That is the That is the angle of soil from the horizontal, and this is the value of soil nailing from the horizontal in anti-clockwise direction. Finite element tool Optum G2 has been used to perform this analysis using the Moore Coulomb model for modeling the soil, and strength reduction analysis has been performed to get the values of factor of safety. Here the basic diagram that has been used in the numerical modeling. This the height of 7 meter has been considered. This is the height. Only this height is considered for we can say for modeling the length of soil nails and all other things. Here the few details of the parametric study, and these are the properties that has been used in the study. Uh, I'd like to discuss that the I would like to discuss that sensitivity estimations have been performed to filter the number of elements that will be required to perform the simulations and to get the exact value of FS. Here you can see after increasing the number of elements from 1000 to 6000 and an interval of 1000 elements each, we get an improvement in the value of factor of safety, and after this value, that is 4000 elements, the value of FAS has become constant. That's why this number of elements has been taken throughout the numerical model to perform the analysis. Now, move on to the next slide. I would like to start with the resultant discussion. This is the basic diagram of the factor of safety with the soil slope with horizontal, that is beta, and KH is the static condition. KH is the static condition, and here K is equal to 0 is the static condition, and KH is equal to 0.12 is the pseudo-static acceleration that has been provided in the direction of failure. Now these are the difference in the values of seismic in the factor of safety before applying the seismic force and after applying the seismic force. There are two analysis has been performed. One is the upper bound and second was the lower bound. And after taking average of both the values, the factor of safety has been decided. Now here is a 3D diagram to show what we get the factor of safety values for a nail inclination theta for the soil slope beta equal to 30 degree. Here we can see that as the spacing of the soil nails increases, the factor of safety decreases with these values. Also, with increase in theta value, the factor of safety increases up to 30 degree for theta value, and after that it also tends to decrease. Similarly, this has been performed for beta is equal to 40 degree and beta is equal to 50 degree. In all these simulations, it has been found that let's say for example, if beta is equal to 50 degree, the soil slope angle, and theta is equal to 50 degree is also the angle of soil nails, then the factor of safety is maximum. Here are some failure plane that I would like to discuss. Here, the length of the soil nails is not seems to be appropriate because the passive inclusion could not be seen, and after that, the values of the length of the soil nail has been increased in order to get the appropriate values of FAS, and this has been performed for all the cases. That is for beta is equal to 30 degree, 40 degree, and 50 degree. And at last, the bending moment and the shear force has been noted in the soil nails. Here M is the middle part, L is the lower part, and U is the upper part of the soil nails. I would like to conclude my PPT. The first conclusion is keeping the diameter of the soil nail constant, the nail inclination of 30 degree gives the maximum factor of safety with respect to beta is equal to 10 degree, 20 degree, and 40 degree. For KH is equal to 0.12 G at 0.5 meter spacing. The FS has been increased by 39.5% than that of the static condition. For 40 degree slope, similar result is found. The factor of safety ultimately increases, and same goes for beta is equal to 50 degree. But two different failure patterns are observed in the study for beta is equal to 30 and 40 degree. The slip circle originated from the slope crest and progresses toward the bottom of the slope. The maximum bending moment is obtained at 1 meter spacing and theta equal to 10 degree. That is the angle of soil nails. And for beta equal to 40 and 50 degree, the maximum bending moment and shear force is obtained as 2 meter spacing and 20 degree nail inclination. That's all. Thank you.
Thank you very much, Mr. Jaiswal. Now, floor is open for questions. I think there may be some question. Professor Costa, can you read out?
Yeah, I just one question to discuss, Sagar. Mr. Sagar.
Yes, sir. Yes, sir.
Yes, for this second conclusion, there's an increase of 50.27% in factor of safety.
With respect to static condition.
So you mean to say that seismic condition is good?
No, sir. Even after applying the soil nailing, in seismic condition, the factor of safety increases than that of the unreinforced condition at static condition.
And the soil that you have taken is I think it's a homogeneous soil or it is a layered soil?
No, sir. It's homogeneous, isotropic.
Homogeneous and isotropic. Okay.
Yes, sir.
So was there any question or it was purely frictional soil?
No, sir. It's quasi soil.
It was purely frictional soil, you considered?
Yes, sir. Yes, sir.
Okay. And did you obtain the pull-out resistance also?
What, sir?
The pull-out of the nails?
No, sir. We're not found that thing because that was not present in the software.
Sorry?
We are also working on, sir, we could not calculate this because that was not present in the tool that we're using. But we are trying to do some more study on this topic.
Maybe you can, that will be whatever you're getting from the software results, you can just validate by doing a theoretical analysis also and find out what is the pull-out strength of the nails. That will be a good comparison between your results, okay? Or maybe the factor of safety, whatever you're getting from this software analysis, you can just using the first principle of that's what we do. You can obtain the factor of safety. Okay, think on these lines also. Okay, just
yes, sir.
Okay, sir, I'm done.
Yes, sir. We are working on this.
There is one question.
Yeah.
In the question answer chat box.
I think, sir, this question is for Miss Ananya. Which elements are considered for the geogrid modeling?
That was, I've also been an author with Ms. Ananya. I would like to answer this. Sixth node Gauss element has been used to model the soil and reinforcements.
Can I have one question, please?
Yes, sir.
Yes,
Sure.
yes, please.
Yeah, sure.
Yeah. Mr. Sagar.
Yes, sir.
See, the factor of safety for static condition and dynamic conditions are different, right?
Yes, sir.
Then how do you compare and say 56% increase?
So that percentage increase has been calculated on the basis of under a static condition and unreinforced condition, and after reinforcing it with soil nails and applying the seismic force.
Correct. See, the factor of safety are different. No, the dynamic condition factor of safety is lower than static condition, right?
Yes, sir. Yes, sir.
Am I right? Then you cannot compare
yes,
and
sir,
say
but
50%, right?
Okay, sir. I will take care of it.
Okay, you can think about that. I think we can move now to the next presentation.
Yeah. And one more thing. Now you are. Yes, sir. Thank you.
Okay, thank you, sir.
Okay, Professor Singh, Dr. Rao, and Dr. Chatterjee. It's almost 7 o'clock here in Japan.
Yeah,
so
yeah.
I think I have to go home. Okay.
Yeah,
so I'm sorry
please.
that I have to leave. Yeah.
Thank you, Professor.
Thank you so much, Hazarika.
Yeah, thanks on behalf of organizing committee. Thank you, Professor Hazarika.
Thank you very much. So enjoy your session. Thank you.
Thank you.
Bye-bye.
Thank you.
Okay, bye-bye.
So much.
Now, friends, let us go for the next presentation. And the next presentation is from Institute of Engineering Risk and Disaster Prevention, Wuhan University, China. The title is Comparative Study of Seismic Slope Displacement Analysis based on probabilistic Modeling of Soil Parameters. And the presenter is Mao Zin Wang. So may I request Mr. Wang to go ahead with the presentation.
Good afternoon, everyone. My name is Mao Xin Wang, and I'm a PhD student in Wuhan University, China. The title of my presentation is Comparative Study of Seismic Slope Displacement Analysis based on Probabilistic Modeling of Soil Parameter. My presentation includes the following 4 aspects. First, introduction. Assessing seismic slope stability is an important topic for many years because the earthquake-induced landslide has huge damage on properties and human safety. It is of great concern in engineering practice. Current methods for the seismic slope assessment can be characterized into 3 methods. The pseudo-static stability analysis is simple, but provides no guidance on the post-failure performance. On the other hand, the stress deformation analysis can drive the stress deformation history, but is complex and time-consuming. So the Newmark type analysis bridges the gap between the 2 methods. The original Newmark analysis assumes the sliding block is rigid, so it can only be used for shallow sliding mass with stiff materials. In contrast, the decoupled analysis can account for the dynamic response of sliding mass, so it can be used in a more general way. The decoupled method first estimates the equivalent acceleration kT, considering only the dynamic response without the slip scenario, and then uses the KT in the rigid block analysis to compute the displacement. In addition to the seismic loading, the soil variability is also an important source of the slope displacement estimation. Slope property varies with location. Some statistical methods, such as the random field model, can be used to describe the spatial variability. The soil properties at different locations are regarded as some random variables, and the correlation among these variables is quantified by a mathematical equation. Generally, 2 properties at a closer distance have stronger correlation. Traditionally, the logic tree method is usually used to account for the soil variability, use 3-point distribution, but it cannot characterize the spatial variability. For illustration, the 2 subfigures show a realization of soil cohesion and the friction angle. It is of great interest to investigate the effect of soil variability on slope displacement analysis based on rigorous probabilistic modeling methods such as the random field model. Let's begin our methodology. As mentioned before, some random variables are used to represent the spatially varying soil property. In our study, we model the undrained shear stream Cu as a random field. Let's look at the 2 figures. The random field can be stationary or non-stationary depending on whether the mean and standard deviation of the variables are uniform or not. Generally, the non-stationary random field is more realistic because we can see the realizations are somewhat more similar to the CPT data in practice. Then the flowchart demonstrates how we consider the spatial soil variability in the slope displacement analysis. First, we characterize the slope geometry and specify the statistics of Cu and other soil parameters. And step 2, we generate random realization of Cu and substitute them into the slope model to perform LEM analysis to determine the yield acceleration Ky and the critical slip surface. Third, we estimate the spatially varying shear wave velocity using a transformation model between CU and VS and perform 1D response analysis using the soil column corresponding to the slip surface to determine the equivalent acceleration KT. And fourth, we just perform the rigid block analysis using the KT. And repeat step 2 to step 4. We can generate a certain number of random displacement samples. So we can then institute the distribution of the displacement and estimate some some metrics such as the probability of exceedance of for some threshold displacement value. A slope with geometry and the statistics of CU shown in this figure is investigated. These are the best estimate values of CU, namely the mean values of CU. Then, after the LEM analysis, we can estimate the yield acceleration as 0.26 g. We have considered 4 random models for comparison. The non-stationary models consider the linear increasing trend, but the RV model ignores the spatial fluctuation. In contrast, the 2 stationary models do not consider the linear increasing trend, but the other things are similar to the non-stationary models. The mean value of the stationary models are taken as the mid-depth value of the CU trend. Let's look at the results about the yield acceleration KY. We have generated 1,000 realization of CU to estimate the distribution of KY. The right figure compares the distribution of KY for different models. As we can see, the random variable models result in larger standard deviation. The box plot is fatter. Also, the random field model results in smaller median value of KY than the random variable models. On the other hand, we can see the general value of KY for the stationary models are smaller than the non-stationary models. Such difference of KY may result in different displacement distribution in the analysis. Then, because we have known the geometry of the sliding mass, we can calculate the thickness, H mass, and the fundamental period, TS mass, approximately. We found the non-stationary random field model produces larger range of H mass, but there is no correlation between H mass and KY. On the other hand, we found a negative correlation between TS mass and KY. Specifically, the correlation for the stationary RF model is stronger, 0.43. Such correlation can be used to generate the random samples of TS mass and KY in the probabilistic analysis. Then we investigate the influence of spatial variability on Kmax divide PGA. 60 acceleration time histories with median value of 0.3 g are used in the analysis. We include the empirical model proposed by Professor Rasaji to compare with our obtained random data. The Kmax divide PGA versus the period ratio is shown in the right 2 figures. We can see this empirical model can generally capture the median trend. But the data for the random field models has larger scatter. On the other hand, the values for the non-stationary models are generally larger. Further, we investigate the influence of spatial variability on the distribution of displacement, as shown in this figure. The displacements for the random field models and the decoupled analysis are larger. Namely, the CDF curves are closer to the right-hand side. Finally, we compare the CDF curves for the 4 random models. The non-stationary and the stationary random field models, the two lines, produce similar results in this case study. On the other hand, the random variable models result in more large displacement data, especially the stationary random variable model. Namely, the dashed line is closer to the right-hand side. Therefore, the stationary random variable model can be considered as the most conservative model. Finally, here are four conclusions. We present a probabilistic decoupled procedure accounting for the inherent variability of Cu and Vs, and compare the probabilistic results for different random models. It is found that neglecting the dynamic response of slope or neglecting the variability of Cu and Vs would yield unconservative displacement estimates. The stationary random variable model is the most conservative model, so it can be used for some critical projects. Okay, that's all. Thank you for listening.
Thank you, Mr. Wang. Very interesting analysis related to the probabilistic modeling, and you have talked about the uncertainties, etc. So now the floor is open for questions. Is there any question from anybody? Any question from the panelists? Okay, if there is no question, Mr. Wang, just one thing I want to know. I mean, here you have considered Cu only.
I also consider the variability of Vs through an empirical model. We just first generate the realization of Cu, and we use the transformation model to transfer the Cu to Vs directly.
So means if had it been C5 soil, then can we use the same model?
Oh, of course, C5 can also be used, but we just consider the Cu in our case study.
Okay. So in that case, means C and phi, they will be considered correlated, or they will be considered independent?
Cu and Vs?
C and phi.
We didn't consider the C and phi. We consider undrained shear strain Cu.
Yeah, that's what I'm saying. Here you have considered only Cu.
Yeah. And the shear wave velocity Vs.
Okay.
Yes.
Okay. So is there any other question? Oh, okay, Mr. Wang. Thank you very much. Thank you very much.
Thank you.
Let's go for the next presentation. And the next presentation is from JUIT Solan by Mr. Amanpreet Tangri, and the topic is strength comparison of flexible materials for stability of slope.
Yes, very good afternoon, sir. So I would be just sharing my presentation. With the kind permission of chair and co-chair of this particular session, shall I start with my presentation? So basically, my topic of this presentation is strength comparison of flexible material for the stability of the slope. So basically, I'm working on the part of soil nailing. So as we know that soil nails are basically made up of steel bars. Those are coated with a cement grout so that we could protect them from those particular bars from the corrosion, and they could be able to transfer the load effectively. So this particular soil nailing is used as a remedial technique so that we could treat certain unstable natural soil slope. And this particular soil nailing components could also be used for stabilizing, like we can use for the retaining walls or for the existing fill slopes. So basically, I had taken a soil which the properties for that particular soil are as follow, and I had prepared a physical model in which this particular soil was used. So water content was around 11%, 2.56 specific gravity, OMG as 7.3, maximum dry density as 1.98 gram per cc, Cu as 5.6, and coefficient of curvature as 0.65. UCS value was 0.118 kilogram per centimeter square, and from this we would be able to conclude that this was basically our poorly graded sandy soil. So the physical model which I had prepared, various dimensions for that model. Length was taken as 60 centimeter, width 40 centimeter, and height was taken as 50 centimeter. It was basically prepared by using a perspex sheet, or we call it as acrylic sheet, whose thickness was 8 mm. So for the application of the load on that particular soil, I have taken a water jack whose capacity is 5 ton. It was consisting of pressure dial gauge, liquid filled ball, and the steel bar which was used as a nails. The diameter of those particular steel was for 10 mm, and the length of steel bar was taken as 31.5 centimeters, so as to we can consider accordingly by FSW that it could be taken as 0.7 h to h. I had considered it as 0.7 h. Flex sensors were used whose length was 2.28. That was basically used to measure the strain, and copper wires were basically attached to the flex sensor and thereafter to the switch, so that and to the multimeter, so that we could be able to measure the strain indirectly by measuring the change in the resistance. Hexagonal washers were provided so that the material could withstand over that particular. Along with that, bearing plates were used whose size was 6 into 6 centimeter, so that the material could be fixed to that particular slope. The slope steep angle was considered as 60-degree, as the flexible facing could be used for maximum of maximum slope angle at a 70-degree. So for that, we had kept it as a 60-degree. Total height of soil wall was 45 centimeter. This is basically the model drawing in which this is basically our loading frame. So from this hydraulic jack was put up. That was basically putting up the load. So these and the nails were basically taken in the three various pattern. Now, how we were calculating a strain in this? So the strain was calculated by using the flex sensor. So indirectly by using the flex sensor, because we were able to measure the changing resistance of that particular flex sensor when the load was applied on it, and there is a formula for finding out the strain as delta R by R divided by the gauge factor. Gauge factor was given by the supplier as 2.1 in that particular flex sensor. So the nail length which we are considering, that was in accordance with the slope height, and its length was length could be considered from 0.7 h to h. So in the present study, it was taken as 0.7 h, 0.7 to 45, that is 31.5 centimeter. Slope was taken as 60-degree in this physical model, and as the flexible material can be used maximum up to 70-degree. So for the scale effect on the soil nails in the granular soil, it's evaluated based on the effect of mean particle size on the shaft resistance. So that there should be no scale effect on the shaft resistance. The ratio of minimum shaft diameter to mean grain size of soil is to be taken, that is d by d50 should be greater than 30. And in the present case, it comes out to be 33.3. So means we are taking this into consideration. Further, facing materials are basically required so that they could hinder the deformation, and thus they could limit the mobilization of shear stress along the nails as well. So we are considering the flexible facing for soil nail so that they can provide restraint to the slope between the bearing plates as well as the erosion control. So in the present search work, I had considered two material, that is HDP, hexagonal slope protection unit, and the biaxial polypropylene unit. So these material are basically chosen because they are having the tensile strength which could be required to balance the tensile stresses which are acting on the slope whenever we are applying the load over that particular slope. So I had considered three nail arrangement, like for 4, 6, and 8 nails were used. 4 were taken in the square pattern, 6 were taken in the rectangular pattern, and similarly the 8 were used in the staggered pattern. So I had used two materials, and these three nail arrangements were used. So first of all, for the first material, so I had considered this hexagonal slope protection unit using 4 nails. So when we are applying the load over that, and when we are able to find out the stress by load by area, so various values of strain which was produced are shown in this particular table. It is from this particular table is seen that maximum strain has been shown in the nail N3 when we were applying the maximum load, and after this particular load there was a failure. Now there is a very beautiful thing about this soil nails, then that when one nail becomes overstressed, these basically distribute the stresses to the other nails before the failure of whole of the slope. So in this case, the maximum strain was basically found in this nail number 3 at a stress of 3.43 Newton per mm square. Next, talking about the 6 nails in a rectangular pattern. Now the stresses were basically stress which it could take before its failure was increased from 3.43 to 5.04, and the maximum strain was seen in the nail number 5. So generally, when the load is distributed from the top to the bottom side, and generally the maximum strains are coming in the bottom nails. Similarly, talking about the 8 nails in the staggered pattern, there has been again an increase in the stresses. Those could be taken up by that particular slope, and it's 6.250 Newton per mm square as compared to the previous of 5.04 and 3.43. And in this, the strain has been also been reduced, but again, the strain has maximum strain is caused in the nail number 7. So mean to say that as we are increasing the number of nails, so there is an increment in the stresses that could be absorbed by the that particular material and before its failure. So talking about the second polypropylene unit, so the stresses which are taken by this particular material was a little bit higher as compared to the first material, and the maximum strain was seen in the nail number 4, that is 1.342. Talking about the 6 nails, there was again increment in the stresses as compared to 4.01 in for the 4 nail, and it was 5.20 for the this 6 nail pattern, and the maximum strain was basically found in the strain number in the nail number 5, that was 0.4195. But there was a little bit different behavior by this biaxial polypropylene unit in the 8 nails in the staggered pattern. So in this case, the maximum strain was taken by the nail N3. This could be basically due to the reason that when the load has been increased, so the nail 3 has become much of the overstress that it has not been able to carry forward the load at that particular point, and therefore there was a failure in the whole of the slope, and the maximum stress which has been taken by this particular uh, material was 6.98 for the 8 nail staggered pattern. So this is basically stress comparison for 4 nail, 6 nail, and 8 nail. And if we compare these both the materials, so this biaxial polypropylene unit has taken up the maximum stresses in all the 3 cases, that is the 4, 6, and 8 nails. So talking about discussion part, so we basically require these facing materials so that they could hinder the deformation, thus limiting the mobilization of shear stress along the nails. So these particular flexural facing also provide necessary strain to the areas of flow between our bearing plate as well as for the erosion control. From the table, we have found that in all of the cases, biaxial polypropylene unit has taken maximum stresses as compared to the HDP hexagonal slope protection unit. In general, both the flexural and your axial stiffness of these facing controls the deformation. So it could be concluded that if we want to compare these two materials for any of the nail pattern, so we can go for the that is your biaxial polypropylene unit. Further, we can also conclude that the flexural facing approach also represent environmental benefits because vegetation could be possible over that particular slopes, and as they allow the growth of vegetation on them, and the use of this flexible material can also provide significant saving if we are comparing with the rigid facing. So, if, as I had told earlier, that if one of the nail becomes overstressed for any of the reason, it will not cause failure of the entire system, but it would be distributing its stresses to the adjoining nails. So, various conclusions which can be drawn from this particular part is that the present study which has been done that could lead to increase the slopes, soil slope load handling and the slope stability. As for 468, we had seen that they are able to take up the hard stresses. So further, this can be used as a construction technique that can reflect even cost effective as compared to a rigid facing. So maximum stresses were taken by the HDP. Sorry, I had mistakenly written over here. Maximum stresses were taken by the biaxial polypropylene unit, and this could be due to the higher stiffness. So these are the various references. Thank you.
Thank you, Mr. Tanvi. Now, is there any question?
So I just wanted to ask one thing, not a question rather. Mr. Amanpreet, you are the student or the supervisor?
I am student.
The student. You are working with the professor's name is
Saurav Rawat.
Savadhan. Okay, okay, that's all.
Is there any question from the panelists? Okay, there is no question. Thank you, Mr. Amanpreet.
Thank you, sir.
Thank you very much. So we now go to the last presentation, and the last presentation is by Dr. Vasant Matsagar from IIT Delhi, and he is going to talk about blast-induced ground motion in geomedia.
Good afternoon, one and all. I am Harshada Sharma. I would be presenting this presentation on behalf of my supervisor, Professor Vasant Matsagar. And the topic of my presentation is blast-induced ground motion in geomedia. So, as the name indicates, the content would be good afternoon, one and all. Good afternoon, one and all. So, I would be presenting on blast-induced ground motion in geomedia on behalf of my supervisor, Dr. Vasant Matsagar. And the content of the presentation would flow as the introduction. The introduction would consist of the ground shock, which is developed because of the blast, and that blast can be of various blast scenario. The stress generated because of this ground shock, the parameters which are very important to predict this ground vibration, that would be in the terms of peak particle velocity, and various approaches which are here with us to predict this peak particle velocity, which would be code-based relations, some empirical relations, and the finite element-based numerical approaches. Then our present study, which we have done, and the conclusions. So basically, nowadays we always see that the surface or ground explosions cause the surface or ground explosions are one of the scenarios of blast or explosion. This can be accidental or man-made blast activities, which can be above the ground, termed as air burst, on the surface, termed as surface blast, or below the ground, termed as underground blast, which releases enormous energy and which generates the compressive waves. These high pressure and impulse persist by these waves induces the ground shock, and this ground shock causes the particle to vibrate in the medium in which they travel. These particle motions leads to ground vibration, and which is generally termed as ground blast induced ground vibrations. So as in figure we can see, if the blast is above the ground, and the shock which is generated due to this air blast, that is termed as air blast induced ground shock. Whereas when the blast occurs beneath the ground, in that case, the shock which is generated beneath the ground, that is called as direct induced ground shock. These both the ground shocks, when the stress pulse is developed due to these ground shocks, and when this stress wave or shock wave propagates in the medium, that medium properties affects the attenuation of the peak particle velocity or the acceleration which is generated due to this shock. The waves which are generated due to various blast scenarios, as discussed earlier, depends upon where the blast is occurring. So that is termed as the blast scenario. In case of air burst or surface burst, the overpressure is generated, and that shock wave front directly hits the structures which are located nearby and cause the damage to the structures. Whereas if the blast occurs beneath the ground, termed as buried or underground blast, which when generated will again harm the surrounding structures, especially the tunnels or the defense related facilities. These buried blasts, or the shock wave which is generated due to this buried blast, depends mainly upon the depth of the burst and the geomedium in which it is going to travel. Also on the weight of the explosive and the radial distance at which the output parameters are to be measured in terms of velocity, acceleration, displacement, or frequency. Again, it may also depend upon the structure overburden depth. Overburden depth is the soil layer which is above these structures, and that pressure which is generated due to this overburden depth also affects these output parameters. When the blast occurs at that time, the shock wave radially moves outwards. When it moves outwards, initially it have incident waves, and when it travels to certain interface, at that time these waves get reflected, and these reflected and incident pressures are to be considered when the underground blast scenario is there. Also, when the geomedium changes, or if the groundwater is also there, in that case also the wave reflections may occur, and these wave reflections are to be considered when considering the output parameters in terms of the velocity, acceleration, displacement, or frequency. So as we discussed, this wave propagation depends upon all these things: the intensity of explosion, the location of the burst, the shape of the charge, whether it is cubical, it is spherical, and the density of the medium. It is very, very important. The velocity of the peak particle velocity, and the medium parameters such as the modulus of elasticity, bulk modulus, shear modulus, compressive strength, and other parameters. These ground shock, when they are generated, they are comprises of body waves and surface waves. The body waves are generally termed as P waves, which are induced due to compression and dilation of soil or rock with particle motion, parallel to the direction of the wave propagation. Whereas S waves are due to the shearing or distortion of soil or rock, and these particle motions are perpendicular to the direction of the propagation of the wave. Normally, surface waves, they dominate the surface or shallow explosions, and far field and also at the far field regions. Far field regions means when the distance between the explosion and the structure is too far. In that case, it is called as far field region, where the near field region is when the structure is located near to the explosion center. Body waves govern the ground shocks for buried explosion or in near field regions. So now the intention is the wave should attenuate. How the wave attenuates? The wave can attenuate with a geometric attenuation or with some historic attenuation. So historic attenuation is the dissipation of energy of that wave, maybe because of the fracture of the rock or the fragments which are developed due to that fracture in which that wave is propagating. The energy dissipation that can depend upon the strength of the geomedium and the geotechnical parameters of the geomedium. Whereas the geometric attenuation, it is dependent upon the propagation of wave and the radial distance in between the explosive and the structure. Radial distance is the distance between the explosion center and the distance where these output parameters are to be measured. There are various ways by which we can find out the output parameters. Here we are considering only peak particle velocity. So there are code-based guidelines which are there. There are some empirical relations given by various researchers in their literature. And there are some numerical simulations through which also we can find this peak particle velocity. This United Facility Criteria, Indian Standard Codes are the two codes which are considered, in which you can see over here that the vertical and the horizontal component of this peak particle velocity is considered same as per the UFC standard. In the empirical relations given by various researchers, they have developed their own formulations to find out the PPV in various geomediums. Here the PPV or VH, VS is the velocity in vertical direction, VH is velocity in horizontal direction, W is termed as the charge weight, Z is the radial distance, and K is the constant, which is a very important parameter for soil and rock. Here we have estimated the peak particle velocity with the help of a finite elements based numerical simulation in ANSYS Autodyne, where we have air and explosive models are generated with in Hillarian base, and the geomedium over here is considered as an Lagrangian. These are the various material properties which are used for air and the various geomediums. The geomediums which we considered are granite, limestone, and sandstone. The properties are considered from the published literatures for the numerical simulations. The multi-material arbitrary Lagrangian Eulerian methodology is adopted because of the various materials which are being used in the analysis. And here we can see that the Lagrangian and Eulerian steps are given. On the same way, the equations for mass, momentum, energy are being given. The velocity, displacement, strain rate is being considered along with the stress. And these were some results which we obtained with these numerical simulations. The peak particle velocity in various geomediums like granite, limestone, and sandstone. These were again compared with the United facility criteria. So we can see that UFC, as earlier, as they do not bifurcate between the geomediums, it is predicting more peak particle velocity, whereas the limestone is predicting more peak particle velocity in the near field region. That means below the scale distance
Miss
of 2.
Harshita, can you please fast, because already we have used your time.
Yeah,
Please
sure,
hurry
sure.
up.
Yeah, sure, sir. Granite and sandstone, we can see that they are having a less prediction for peak particle velocity in the near field region, whereas when we go for far field region, the vice versa results are observed. These are some upper and lower bound values for seismic velocities for various geomediums, and we can see that these are the main important factors for the attenuation of the shock wave. Then how the arrival time is there of the shock wave, that is also considered in this study. And we can see that the time of arrival is higher in loose soil, which shows that the wave propagation is faster, is loose in which shows that the wave propagation is faster in hard or intact rock. We can see over here that the loose soil is having the more time of arrival, whereas the other sandstone or other soft or hard rocks, they are having less time of arrival. These were the some vertical and horizontal velocities compared with the published literatures with the experimental work which has been done in that paper. Finally, the conclusions in which we consider that the UFC shows invariably higher estimation of PPV in comparison to the IS codes and the numerical results. The limestone shows higher stress transmission with significantly higher peak particle velocity in comparison to the other rocks. The loose or poor graded soils or weathered rocks can be effectively used to attenuate more and delay shockwave arrival to reduce the catastrophes during accidental or man-made explosions. The vertical and transfer components of estimated PPV with our analysis, we found that the variation is near about 40 to 37% respectively, whereas the code-based guidelines predict equal magnitude for these peak particle velocities in regardless of vertical or horizontal directions. These are some references which are being used. Thank you.
Thank you, Harshada. Maybe one question we can take half a minute.
Yes.
If there's any question. If there is no question, then thank you, Harshada, very much for your presentation.
Thank you, sir.
And now we have completed all the presentations, and we have also exceeded the time. So maybe another 1 minute or 2 minutes, the co-chair can briefly conclude it, and then we hand over it to the organizers.
So overall in this session, we had one SOP lecture that was given by Professor Hemant Hazarika from Kyushu University, Japan, and 5 contributing papers. All the papers were really focused on giving great knowledge to the listeners. And summing up, the main thing that we had in this particular session, we can see that in the SOP lecture, Professor Hazarika spoke about the evaluation of long distance flow in a lateral, the long distance lateral flow in a sloping grounds wherein due to the effect of 2018 Sulawesi earthquake of Indonesia, and it was observed that in that particular the short period, components had played a very important role. Okay, coming to the present paper presentations, the first three papers were basically focused on reinforced soil structures, like studies on the geosynthetic reinforced retaining what, and other one was the slope displacement. I mean using the numerical studies on soil nail slopes. Okay. Next, we had a presentation by Mr. Wang from Wuhan University, China, who spoke about the slope displacement analysis based on probabilistic modeling of soil parameters. Again, Mr. Amanpreet Tangri discussed about the stability analysis of nail soil slopes using flexible materials, and where we have carried out some experimental analysis. Lastly, the final presentation by Ms. Sharma was on the blast-induced down motion in a typical geomedia. Okay. So overall, we thank all the speakers for their excellent presentations. Okay. So with this, I think we can close this particular session.
Okay, thank you, Professor Pastor. Now, it's my privilege to say thanks to the organizers for giving us this opportunity to be with you and organize this session. Thank you very much, and we thank all the participants and the speakers who have spoken and shared their expertise and work of research. So with these words, may I close, Dr. Raghuveer, the session?
Yes, sir. Yes.
The
Yeah,
session
I will
is
just.
closed.
Yeah,
So
yeah.
the session is closed, and now I hand it over to the organizers.
Thank you, sir. On behalf of the organizing committee, I thank all the speakers and the chair, co-chair especially for timely completion of the session. Thanks, sir, on behalf of organizing committee. Thank you very much.
Thank you.
Thank you, sir. So we'll meet at 4:30 for the plenary session. Thank you.